Hi, it's Mr. T here. In this video, we're going to look at temperature and how temperature relates to particles and how we can use this to explain some phenomena we might see in the everyday world. Now, this is part of the Achievement Standard 3.4 for Level 3 NCEA, and specifically about the transfer of heat between systems and their surroundings. Right, Brownian motion, what is it? In 1827, Robert Brown, he was engaged in looking at pollen from vegetable juice from plants. Now, as he looked down the microscope, he could observe the little grains of pollen. But what he noticed is that these grains had small, tortuous movements. They just moved randomly across the place. And in honor of him, we call these small motions of pollen or dust particles on the surface of liquids Brownian motion. Now, the reason that these small pollen particles or dust particles randomly move is that the particles in the water are randomly moving themselves. And this is because all particles are in random motion. They have a random velocity, and which means they have a random direction and speed. Okay, so if we were to take any substance, the kinetic energy, or the average kinetic energy, and that is derived from the velocity of the particles, the average kinetic energy of the particles is the same independent of the substance. So if you had, let's say, some water and it was at 25 degrees, the water would, each particle of the water would have an average kinetic energy. And if we had some oil, each particle would have the same average kinetic energy. Or if we look at a mixture of air, all the different particles in air have the same average kinetic energy. Now, because of that, we can relate the kinetic energy to the velocity using the equation Ek equals half mv squared. Now, there is a proportionality in the statement between the mass and the velocity, and if I rearrange this equation, we find out that the velocity of a particle is 4 times smaller if its mass is doubled. So if you have a particle that's twice as big as another one, its velocity is going to be 4 times smaller, or the reverse, if the particle is half the mass of one, its velocity is going to be 4 times bigger. Therefore, because of this equation, particles with smaller masses will move faster than particles with larger masses at a given temperature. Now, this is an important idea, and this is used to understand diffusion. So smaller, lighter particles with a smaller molar mass will diffuse faster than heavier particles. So there's a nice simple demonstration we can do to show this. So I've just got an animation of this. So if we were to take a long glass tube and put on one side of the glass tube, put a cotton swab with ammonia solution dissolved in it, and on the right hand side we had another cotton swab with hydrochloric acid dissolved in it. Sorry, concentrated hydrochloric acid wetting this cotton. What would essentially have is the ammonia would give off ammonia gas, and hydrochloric acid would give off hydrochloric acid. Now, because the ammonia has a molar mass of 17 and the hydrochloric acid has a molar mass of 36.5, the ammonia is going to move or diffuse. The particles will randomly move 4 times quicker because they are half the mass, so they're 4 times quicker, their velocity. They are going to move 4 times quicker than the hydrochloric acid, and the ammonia and the hydrochloric acid will react together to produce a solid ammonium chloride. This solid will be observed as a cloud in the tube. So if the ammonia should react 4 times quicker, move 4 times quicker than the hydrochloric acid, where will these two clouds of particles meet? And where they'll meet, we'll see a white cloud. Where do you think on this tube that they'll meet? Just see if you can point to it. This is where they'll meet. So the ammonia will travel a lot further than the hydrochloric acid. They both have the same kinetic energy, the same temperature, but because they have the same kinetic energy and the ammonia has half the mass, it will travel 4 times faster. So this is really important for understanding that smaller molecules will diffuse more quickly, or they will escape from confinement more quickly than heavier molecules. We all know that if we get a helium balloon, or we fill a rubber balloon with helium, that the gas is going to move out of the balloon more quickly than would be if we had just filled it with air. And that's because helium is a lot smaller than the nitrogen particles or the oxygen particles in air. Okay, so what is temperature? Well, remember the particles in a substance have a range of different velocities, or kinetic energies, because velocity is directly related to kinetic energy, due to their Brownian motion. Now, how does Brownian motion, remember we talked about the pollen moving on the top of a liquid. Now, that is just, if you think of someone, I guess, playing pool or snooker, and they were to break the pool balls or hit the white ball into the triangle of balls, then all the balls would bounce off and hit each other, and they would be going at different velocities. That's essentially what Brownian motion is inside a substance. So all the particles are moving at different velocities. However, they do, if we were to take all of those different kinetic energies associated with those velocities, and we were to take the number at each kinetic energy, we could plot them and we would get a normal distribution, or a bell curve. This normal distribution shows us that there is an average kinetic energy, and we can associate a given temperature with that. And in this case, the average kinetic energy in this graph is 20 degrees Celsius. We can also see that there will be some particles that have more kinetic energy than you would have for 20 degrees Celsius. They might have the same kinetic energy you would have for 80. Some might have the same kinetic energy you would have for -10. There is a normal distribution. There are some particles that will have more kinetic energy than you would have for 100 degrees Celsius. This is important because we're going to use this idea to explain how evaporation happens. If we increase the temperature of kinetic energy, the kinetic energy of the particle of a solution, the kinetic energy of the particles in the solution increases. So if we look at this graph here, we can see at temperature 1, here's an example of a container. Here's some particles I've highlighted. They have random motion, so they've all got these vector arrows showing their direction of their velocity. So they have a random kinetic energies. Now at temperature 1, they have less kinetic energies, but if I increase the temperature, we now have the vectors are larger, so I have a higher proportion of my particles have higher temperatures or kinetic energy. And notice also the average is increased. So if we increase the temperature of a solution, what we're essentially doing is we're increasing the kinetic energy and hence the velocity of the particles in the solution. And if we look at it in the way of a normal distribution, what we're doing is we're moving the normal distribution curve further to the right, making the average a higher temperature. Okay, what is evaporation? So at 25 degrees, we have a normal distribution that looks like this. What we can see here is if we put a cutoff here at 100 degrees Celsius along the bottom axis, we can see that there is a proportion of the particles that actually are above 100 degrees Celsius. So these particles have the kinetic energy that is equivalent to 100 degrees Celsius, even though the solution isn't on average at 100 degrees Celsius. The solution on average is 25. There are some particles, because the particles can bump into each other in random motion, some can bump behind others and actually give them more energy than they initially had. Now this will, if these 100 degree particles are on the surface of the liquid, well, no matter where they are, they will change phase if they're above 100 degrees from liquid to a gas, okay, because 100 degrees is the boiling point of water. So if we're looking at water, this would change the particles from a liquid to a gas. Now, if these particles are inside the substance, once they turn to a gas and they hit another particle, they will lose some of the energy and turn back to a liquid again, so nothing will happen. However, if the particles are located on the surface of the liquid, then they will escape into the air and they will be lost from the whole solution. If you take away all of the heavier particles in the solution, what do you think will happen? Well, what will happen is obviously the amount of solution that you have or substance will decrease, and this is what evaporation is. So at 25 degrees, that's the temperature well below the boiling point, you will still have particles escaping into the gas phase as evaporation, and what you will have is you will have the total amount of particles decreasing because you're taking away the particles that are larger than 100 degrees on the surface. And that's how evaporation would happen in a puddle. If we were to go outside and see on a sunny day that there was a puddle at the start of the day, and at the end of the day the puddle was a lot smaller, that's how evaporation occurs. Okay, so what actually happens if you take away the higher energy particles? Well, so let's say we had a solution at 60 degrees Celsius. The higher degree particles here, I've put a blue line, this is the 100 degrees Celsius line. And so all of the particles that are above that, if they're on the surface, are likely to go and escape from a liquid to a gas. They are going to turn into the gas phase from the liquid phase because they have enough kinetic energy to do that. Now, if I take away all of these particles on the right hand side, then what's going to happen, my average kinetic energy of what's left is now going to redistribute. And because what they'll do is all these particles are left will go around bumping into each other, and on average their average energy is smaller. I redraw this bell curve and now I have less particles that are over 100 degrees. So when something evaporates, essentially what happens is the substance cools down, or the solution cools down. This is really important. We use this as a cooling mechanism on our skin. The water on our skin will evaporate. As it evaporates, it takes energy from our body, so it takes heat energy from our body and cools us down. So actually, if it was on our skin, what would happen is the liquid would disappear over the particles over 100, with the kinetic energy equal to 100 degrees Celsius. Then we would get this where the water was actually a smaller temperature, but then we would heat the temperature up until more would evaporate, and eventually it would all disappear. Anything that is evaporating, we would essentially see it getting cooling unless more energy was added to it. Anyway, I hope this introduction to kinetic theory and evaporation has been useful. Look out for the next video that I will do on phase changes.